You know the old saying, practice makes perfect. Well, I've put together a few examples to illustrate the techniques of finding probabilities for normally distributed variables. Let's get some experience using z-scores to answer questions about normally distributed variables. In the first example, we are told that the length of time a woman is pregnant is normally distributed with a mean of 260 days and a standard deviation of 15 days. And we're asked three separate questions. What proportion of the women are pregnant for less than 234 days, more than 265 days, and finally between 250 and 270 days? This will require three separate analyses, but there'll be many similarities between them. The first question posed was less than 234 days. So we compute a z-score using the hopefully now familiar formula by taking the value in question, namely 234, and subtracting the mean of 260 and dividing by the standard deviation of 15. The calculated z-score is a negative 1.73. It is negative because 234 is below 260. So now we're going to go to StatCrunch's online normal calculator, and we're going to enter the minus 1.73, and the reported area is 0.0418. So 4.18% of the pregnancies come to term in less than 234 days. The next question asks more than 265 days. So now our x value is 265. The mean is still 260 and the standard deviation 15, and that cooks up to a z-score of 0.33. Again, we're going to use StatCrunch's online normal calculator, and it reports back that 37.1% of the pregnancies take more than 265 days. The last question is between 250 and 270 days. This requires calculating two z-scores, one for 250 and the other for 270. This time on the StatCrunch calculator, we're going to switch from standard, which would be either below or above a specific z-value, to between two z-values. And now we are entering the z-values of minus 0.667 and positive 0.667, and StatCrunch reports back a probability of 0.495. So 49.5% of the pregnancies last between 250 and 270 days. Next example concerns a very pricey sports car, the Porsche 911. It's in high demand, even though its cost of $87,000 new. It has a resale value of $48,000 3 years later. So it's definitely out of my league. So here's the question. Suppose the prices of 3-year-old Porsche 911 sports cars are normally distributed with a mean price of $48,125 and a standard deviation of $1,600. Find the probability that a randomly selected 3-year-old Porsche 911 will sell for a price between $46,000 and $49,000. So as you suspect, we're going to have to calculate z-scores corresponding to 46 and 49,000 using the mean of 48,125 and the standard deviation of 1,600. Using that StatCrunch calculator I spoke about, we're going to then translate that into the probability that Z is in between negative 1.33 and positive 0.55. And the calculator reports back that that percent is 61.7%. So here's a screenshot. Here are the two Z values of minus 1.33 and 0.55, and here is the reported probability of 61.7%. So there's a 61.7% chance that a randomly selected Porsche 911 will sell for a price between $46,000 and $49,000. Now I'm going to tell you a little secret. In the previous applications or demonstrations, the mean, of course, had been set to 0 and the standard deviation 1 because we were calculating z-scores and we were using the standard normal curve. There's actually a little way to cheat. You can change the mean to the actual mean, in this case 48,125, and the standard deviation of 1,600. And instead of calculating z-scores, you can enter the actual boundary values of 46,000 and 49,000, and not surprisingly, you get the same probability of 61.6% chance. Now, the math textbook is not going to talk about this, but it's a little secret that I'm going to share with you. So our next example is talking about a toy, and the normal assembly time for this little toy is a mean of 55 minutes and a standard deviation of 4 minutes. The company closes at 5 p.m. every day. If a worker starts to assemble a racing car at 4 p.m., what is the probability that she or he will finish the job before the company closes for the day? So on average, it takes 55 minutes to produce the little toy with a standard deviation of 4 minutes. What's the chance you'll complete it in an hour, in 60 minutes? So we're going to calculate the z-score corresponding to 60, which turns out to be 1.25. We want to know the chance that we will complete the toy in less than 60 minutes, which is equivalent to asking what's the probability that the z-score will be less than 1.25. And once again, our little normal calculator reports back that's going to be an 89.44% chance. So I have two screenshots to share with you. The screenshot on the left is where I enter the z-score. The z-score being, let me see what the z-score was. Let's go back for a second. The z-score was 1.25, so I entered the probability that z would be less than 1.25, and we come up with this 89.4% probability. And then I cheated a little bit. I entered the true mean of 55 and the true standard deviation of 4, and asked it to calculate the probability that the time to complete the toy would be less than 60 minutes, and of course we get the same answer. My final example has to do with soft drinks. A particular corporation produces many types of soft drinks, including an orange cola. The filling machines are adjusted to pour 12 ounces of the soda into each 12-ounce can. However, the actual amount of soda poured into each can is not exactly 12 ounces. It varies from can to can. It can be observed that the net amount of soda in such a can is normally distributed with a mean of 12 ounces and a standard deviation of 0.015 ounces. What is the probability that a randomly selected can of orange cola will contain between 11.97 and 11.99 ounces of soda? So before we get to the next slide, I'm assuming that you know we need to calculate z-scores, 2 of them, corresponding to each of these boundary values. In here are, we have our boundary values, our mean of 12, our standard deviation of 0.015. So we have reformulated the question to ask, what is the chance that z is between -2 and -0.67? And the next slide shows on the left my entering those z-scores, -2 and -0.67, on a standard normal curve with a mean of 0 and a standard deviation of 1, and coming up with 22.86% chance. And then I'm cheating a little bit, and I'm entering the actual mean and the actual standard deviation and the true boundary values of 11.97 and 11.99, and of course coming up with the same answer, that there is a 22.87% chance that we select an orange cola can that has between 11.97 and 11.99 ounces of soda.